Thank you so much to participate to this panel. My name is Bernard Bigot, and I am the Director General of the ITER organization, where we are building the largest facility research on fusion in the world. So we are very grateful to the conference of the party, as well to the UK host, to welcome us in order to introduce what could be the shared hydrogen fusion for combating climate change. So I guess we will have very soon an introduction of the four other panelists, which will be introduced. Could we? Okay, so the slide with the panelist is not yet. Yes. So first, we have the pleasure to have Mrs. Anika Khan. Could you raise hand? Thank you. At Manchester University. The next is Professor Sibyl Gunther, which is the director of the Max Planck Institute for Plasma Physics in Germany. A very well-known, worldwide qualified person. The third one is Mrs. Amanda Quadling from UK Energy Authority. Thank you. And the last is Jane Oskich, which is sharing energy for the common good. And we thank very much all of you to participate. Combating climate change is not a competition among clean energy sources. It will require complementary effort for all the qualified contributors. We need all that we urgently to have to replace the fossil fuel on a massive scale. Hydrogen fusion over an ideal energy source as a key part of the solution. First, it is a natural phenomenon. It has been working for 1 billion of years in the sun and the star, and there is enough fuel there for further 1 billion of years. For now, more than 100 years, we have understood better and better the physics of fusion, since it was discovered that the sun was made of hydrogen, a big bubble, 300,000 times the weight of Earth, and helium. And the physicists imagine that the hydrogen transforms to helium by fusion. In recent years, fusion R&D has made tremendous progress. It is a testimony that progress where we are today for the first time at this conference on climate change. Today, we hope we will discuss with the capacity of delivering fusion power and demonstrate it is greater than ever before. We will also examine, challenge technological, financial, and regulatory challenges, and also to try to explore how international cooperation and public-private sectors and partnership will be so important. So, if you agree, let me give the floor to the other panelists. And the first will be Annika from the University of Manchester. Tell us about how fusion works and what makes it so desirable as an energy source for your generation.
Thank you, Bernard. So, as Bernard's already touched on, there's a huge, we need to be trying everything. All throughout COP, we've been seeing different solutions that are being put forward, renewables, we've got young generation nuclear here today. These are all things that we need to be doing now in the short and medium term. Where fusion comes in, that's a more long-term thing. We need to be able to develop technologies and energy that will be there as a stable baseload to complement these other technologies, such as renewables, such as traditional nuclear energy. Traditional nuclear energy relies on fission, which is the splitting of atoms to release energy. Fusion is kind of the opposite, where you fuse atoms together, liberating huge amounts of energy. As Bernard says, this is what happens in the sun. Why is that good? It's low carbon. The fuels that we need to use are isotopes of hydrogen, deuterium and tritium, which are quite plentiful. Deuterium can be found in seawater, and tritium can be extracted from lithium. So we have this fuel available to us. So fusion's great because it's low carbon and the fuel is plentiful, and it has that capacity to provide a stable baseload when it's not windy, when it's not sunny. At the moment, that role is being taken by fossil fuels, and we need to stop that. And we also need to make this technology available globally, because I think one thing that people always forget is that there's still a huge inequality in access to just energy in general, wherever that's coming from. And if your option is having no energy or fossil fuels, you're going to go for fossil fuels. So we need to be very, as a fusion community, we need to make this accessible to everyone so that everyone has a stable, clean baseload of energy. And that's where fusion comes into the picture.
Thank you, Annika. If I may add up, is why I say they could be very well complementary or renewable. You could start the plasma and stop the plasma whenever you want. You see, when the wind is not blowing, when the sun is not shining, okay, hydrogen fusion could take over to keep, okay, the energy supply for the planet. Very big advantage. So thank you so much, Annika, again. And I give the floor to Sibyl. Sibyl, would anyone else would like to mention why, if fusion is so great, we have not so much power plant connected to the grid?
Fusion is great, in particular in the sense that, like Annika said, for example, we need really a very small amount of fuel, so you can take a kilogram of deuterium tritium and can power 1,000 people for a year. So this is really something you really need, otherwise tons of coal. But the question is, of course, appropriate, and if it's so great, why don't we have it yet? The reason is that the challenges are also very great, and one challenge has been shown in the video to you. We need to achieve temperatures 10 times higher than in the solar interior, which is 100 to 200 million degrees. For example, and enough particles to fuse, and we need a good energy confinement, that is heat insulation has to be better than polystyrene. We did achieve already a lot. We did achieve, for example, the very high temperatures. So we put the plasma into cages of magnetic fields, And even in our small device, with a small radius of a donut of 50 centimeters, we achieve 200 million degrees here and 1,000 degrees Celsius where you have the metallic walls, right? So this we have achieved already. We also have achieved sufficient number of particles there to fuse. We have not yet achieved a good enough heat insulation, but there's a figure of merit including these three quantities, so temperature, density, number of particles per volume, and heat insulation, and we achieved since the last 50 years a factor of 10,000 to improve. So it's not that nothing has been achieved yet. There are still enormous challenges. Some will be met, Bernard is responsible for that, will be met in ITER. So in ITER, for the very first time, we want to achieve a kind of self-sufficient plasma. That is, the fusion energy is then the major part of heating the plasma. In fact, it should have 10 times more energy out of fusion reactions than you put into the plasma to heat it. I'm convinced actually that this is easy to achieve in a sense. We will be better in ITER, I'm pretty sure, because our present-day devices go beyond that already. Not that we can achieve it, but the parameters for that. So ITER will be showing that. For a power plant, we need not a factor of 10, but 50 to 60. I'm pretty sure we can manage in ITER. And we want to show that we can really get the fuel out of the tritium out of the walls. But there are remaining challenges as well. We want lung pulses. We want reactor-relevant heat insulation to allow us for an economic design of fusion power plants. And besides physics, there are many technological challenges like development of materials. So you have to withstand these high heat fluxes. If you don't do anything, it's the heat flux at the sun's surface. You want kind of low radioactive waste, at least not long-lived. We want to have high temperature superconductors, so not needing helium to cool it down, have high magnetic fields, and other challenges. And materials, Amanda is much more an expert than I am.
Thank you. In order to maybe make easy to understand why it is a challenge, size matter. If the volume of the plasma is not large enough, you will not be able to have a self-heating plasma from the helium nuclei, which is produced with 5 times more energy than the collision. Is why one of the major challenges we have now at ITER is to assemble all the equipment in order to sustain a plasma with a volume of 830 cubic meter, while the largest one now is 80 cubic meter. So for me, the challenge is size and precision, because we have to have, with the magnetic gauge, very high precision. So I know many people are impatient, but the breakthrough will be so large that it will be rewarding to be patient. If anybody want to comment? If not, I will give the floor to Amanda.
Bernard, thank you. I want to talk a little bit around the UK because we're hosting here COP26 this year and very proud to do so. And you've heard already that there's an urgent need for fusion and some of the technical challenges around what we still have to get right before we deliver fusion. But we have to start to prepare now for the fact that we are going to deliver fusion. And so I want to talk a bit about what a national policy looks like, or a national program, and all the different facets that are required in order to deliver fusion. So you need your government, first of all, to be supportive, and the UK government is doing exactly that. In the last couple of months, we've put out a white energy paper talking to the Net Zero programme and how fusion can be part of that. And then just in the last few weeks, a fusion strategy paper itself. And that strategy paper contains a commitment to deliver a power plant, a demonstrator pilot power plant that will put some energy into the grid by around 2040. That's a significant commitment for a national government to make. And it recognizes, that strategy document, that in tandem, you'd probably have to have a significant supply chain and industry to support the delivery of the power plant. So that is the second of the two commitments in that strategy document, that we have a growing body of technology developed locally that will allow us to export and helps with the economy, but that then enables the delivery of that power plant. The fact that it's a demonstrator, what is it going to demonstrate? It's going to demonstrate commercial feasibility, which means low cost and reasonable scale. So there are some very specific factors around that demonstrator. We've called it STEP, and STEP as a program is already underway. The government has put £220 million behind the first tranche of concept development, and so that is the policy position. You then have regulation. Anything that is around energy has to be properly governed, and the regulatory regime that we're looking for is again going to be highly creative. We're looking to take a trajectory forward, which we've already begun with in Fusion in the UK, and that is that we are governed by the Environmental Agency and our health and safety body. It's a pro-innovation regulatory framework. It recognises that we want to be goal-orientated rather than rules-based, and it is very proportionate to the fact that fusion is a low-hazard process. It has no chain reaction, and therefore we can afford quite a creative regulatory environment. There is, at this moment in time, a consultation out publicly. The government is looking for feedback from industry, from academia before Christmas. There's also the plan to put a fusion cluster into the UK, because you need that supply chain developed, and we need the public-private partnerships, and to enable them, this cluster will bring people together in shared facilities. It'll be a focus for the investors to come together, and it will be a focus for the researchers to come together to share their learnings. So mobilizing, mapping the supply chain is part of that cluster, and so is a grant award program, the Fusion Industry Program, that will give money to researchers to develop new technology for fusion. So I've talked about the policy, and I've talked about the regulatory framework. The third and very important pillar is that of the technology itself. And the UK has been involved in JET, the Joint European Torus, for a number of decades. We're very proud to have hosted it at Culham in Oxfordshire. It is generating DT, deuterium-tritium data this year as part of its campaign. That data is flowing to ITER in order to help with the commissioning of those first plasmas in 2025. We're very proud to have been a founding member of ITER, one of the 35 member states in ITER, and so it is very much a collaborative effort. So probably more than anybody else, Bernard, you're the person to comment on the power of the collaboration that comes through ITER.
So thank you so much, Amanda. Yes, this is definitively cooperation is key, and so is why I would like to come to you, Jay. Now, we hear about that quite a lot of the news about the growth of private support for fusion. Companies in the US are demonstrating that more and more people are convinced that we are at a turning point where it is very likely that private investors are worth to put their money in fusion. Could you comment on that?
I'm happy to, and thank you to the UK EA, to the UK partnerships, and to the COP26 organizers, because this event right now is one of those milestones in the change in fusion energy. We're right now witnessing fusion energy's involvement in the climate discussion. And up until now, that's never happened. So it's a privilege for me to be here as a US citizen, as a former developer of wind and solar, as an NGO, often asked, why am I in the middle of fusion when fusion doesn't exist yet? And in the US, it's starting to feel as if it's a pre-commercial space. And that's in part because we're seeing enormous numbers of investors come in to support 30 or more private companies situated around the country, in approaching both fusion device builds, and when I say fusion device, remember these are a multitude of different technologies. The fusion sector isn't just one type. It has multiple types. Not all of them are going to work, but just as we start with any technology, this is the beginning. And the technology that's best known because of ITER's strength, because so much of the global knowledge has been developed in partnership through ITER, and because of the advances that the UK has made and other governments around the country, around the world have made. But in the US, as is typical, it's the private sector that's now goading our public sector. So we have a number of leading investors coming in, followed by a host of others. They're following two major things. One, technology changes, and two, the reason we're all gathered, which is climate change. This impending disaster that we are all approaching with hope and with attempts to combat. So fusion's promise as a mitigation to climate change, it has attracted many. On the technology end, we're talking about materials that have changed or new materials that have entered. We are talking about computing, supercomputing, and we're talking about manufacturing, 3D manufacturing, which allows you to build things that you could never build before. The channeling that you need to build, for instance, a tokamak. So you're seeing enormous amounts of money come from, well, just this last week, a West Coast private fusion company announced $2.2 billion in committed investment. Now that dwarfs what we've seen in private-public investment globally. Now, again, we're still on the road, but we're also seeing headlines. Headlines of successful tests, such as the magnet test in my hometown, Boston, by Commonwealth Fusion Systems, that delivered beyond imagination and is part of its path to net zero. Again, why am I doing this? Because climate change is my organization's sole purpose, and we know we need a lot more energy than can be produced by wind and solar, my personal background. Because electricity only represents 18% of global energy use. So if we made it all from wind and solar, we wouldn't tackle climate change, the energy system's impact on climate change. And fusion's promise to bring in both industrial high heat needs, so for concrete, as well as transportation fuels, makes it we often call it a potential disruptor. And that too is why so many of the private investors who have made their money in plasma physics, in other sciences, are coming in to support fusion.
Thank you very much, Jane. If I may comment myself, I have been working for ITER now for nearly 20 years. 20 years ago, no private investment. Everybody was skeptical in some way. Are you able to assemble a large magnetic coils cage with a vacuum vessel, 20 meter large, 20 meter long, with a precision of millimeter? Now, since we are 75% completed towards the first plasma, we see more and more interest. People say, whoa, if this fellow succeed, I don't want to be behind. And it's why it's so good to have all these complementary projects improving technology, material, operation, information, and control. And we will work together in order to make it successful. So, I will come back to you, Annika, if you don't mind. You have achieved a lot so far as a young leader in the fusion. Tell us what fusion means for your generation available for the younger generation to get involved, including ladies.
Thank you, Bernard. So as all the panelists have said today, we're in a real transition phase in fusion. From when I started almost 10 years ago, we're seeing a real move from it being purely science-based, purely research-based, to being much more applied, engineering, and a lot of other opportunities are available. And we need people working on it. There's not enough people working on it. So we have all the technical challenges that have been mentioned, so engineering, materials, physics. Those are big opportunities for people to get into. But going forward, Amanda mentioned regulation. That's going to require people with those skill sets as well, being trained in the legal framework and policy and things like that. That's going to be vital going forward. And what we're doing today, communication. The public don't have an awareness of what fusion is. If they don't have an awareness, they're not going to trust the technology and they're not going to know what it is. We need people who are good communicators. And actually, our young people are the best asset. They're doing it already off their own back. They're just so talented at sharing that message and making fusion known to the world, which is so important and what we need right now. We need to make more opportunities. We need to start younger on. So I think we need to start educating people even in primary school, secondary school about this technology so that they're just aware of it as a career path and a viable option for them. And we need to be doing that globally. We can't be just, we're doing it here in the UK. That needs to be done in developing countries. It needs to be a particular focus on women as well, because although the panel today is mostly women, this is not a common sight in our industry. And we need to make sure that there are more women involved in this. And like I said, particularly from developing countries. So to summarize, a lot of technical opportunities, a lot of engineering opportunities, also crossing over to other fields. As Jane mentioned, it's not just for energy, maybe having a role in the hydrogen economy or kind of manufacturing and things like that as well. There's a lot of crossover. So we need those technical skills. We need people who are good at policy and legislation, and also communication is key and education is key.
Thank you very much, Annika. If I may just comment, as the ITER organization Director General, I receive many applications from the June generation. And very often they tell me, I want to be serious about the climate change issue. My contribution to solar panel, to windmill, is ongoing. I want to be in the disruptive breakthrough. Please apply and join us. So, Sibyl, if you have opportunity to tell us if there is more than a way to bottle a star, as you know, can you explain some of the different approach to fusion, and which one do you prefer?
Well, yes, thanks, Bernard. I mean, we have been investigating how to bottle a star since many, many years. And in a kind of Darwinian process, we have down-selected actually two approaches. One concept is the tokamak, like ITER, and this is the most advanced approach, and therefore ITER will be the first device to demonstrate a self-sustained burning plasma. There have been other approaches, and the next advanced approach is the stellarator, and we have just recently built a big superconducting device in Germany. And the stellarator is lagging behind the tokamak, and that is because the magnetic field cage of a tokamak is kind of simple. It's axisymmetric. In the stellarator, you have to really, you need the superconductors Jane just mentioned to optimize the magnetic field cage to keep the plasma in. So this we did, and so we did build a superconducting stellarator in Greifswald recently. And so so we don't know yet which of the two concepts will make the most economic fusion power plant. I'm pretty convinced both would make it. So we are excited now because we just start operation next year again. And so I would not put all my eggs in one basket. I love to see ITER succeeding, and we also work on tokamaks in Germany, so there's no division. But I would like to be the next step, ITER-like device, be a stellarator, and then choose what is the most economic power plant to make fusion work. They might both survive like car engines, right? There are also two types. or we might in the end find that one is more economic than the other. The major advantage of the stellarator is that it would be steady state and not running in pulses. Also, you can also have a pulsed power plant. So I'm very interested to see which one will make the race.
Everybody has to understand, in order to have a stable plasma, you need to twist the magnetic line. So there is two ways of twisting the magnetic line. Stellarators, where you twist the magnetic coils. Quite challenging. The other way is to twist the magnetic line with a central solenoid. But the central solenoid could not increase the magnetic field up to the sky. You have to stop at maximum and come back. But from my point of view, the two has very good option, certainly. So, thank you, Sibyl. Amanda, yes, how would you see the contribution already being made to the fusion research by the world, scientific community, in particular in material science? As you know, fusion want to make the demonstration of this technology and offer this technology for all the countries. Certainly, to make the demonstration is mainly the most advanced countries which could do it. But once it is done, we will put everybody on board.
So I think it is a beautiful way to tie up your question about how we make this a global and not just a global north solution, and what Sibylle has just shared in terms of stellarators and tokamaks, because there are also two types of tokamaks at the moment that are being developed. There are those in what we'd call a traditional donut-shaped torus, and then there are also those that are more spherical, and each brings their benefits from a physics point of view. So if I talk a little bit about what the Global South has been doing over the last couple of years, it's quite interesting how creative the Global South has been. Brazil has 3 tokamaks at the moment, or devices that it's been running over the last couple of years. And I didn't realize until recently that one of them at the Space Research Institute is actually a spherical tokamak. That's the same route that UK is taking at the moment with our STEP demonstrator, is that it's a spherical tokamak. That's one of the 3 devices. They have 2 others. And those other 2 devices, one was built with the help of Japan, and one was built with the help of Switzerland. And so I think already you have a perfect example there of Global North and Global South working together around these experiments that cost a lot of money and a lot of effort. And then if you swing, in terms of the Global South, from west to east, and we talk about Australia for a moment, Australia ran a stellarator for almost 30 years, from the early 1990s.
We are collaborating with them.
There indeed. So again, we have the North-South, and again, we have the fact that the South is quite creative in what it attempts to do in its experiments. And Australia also, as a non-member state, chose to affiliate with ITER in 2016 and get themselves a collaboration agreement which gives them full scientific and technological cooperation rights in ITER. And I think going forward, that's what we're going to see. ITER is a very big project, and it's a fantastic platform to bring global North and South together for transfer in and out of skills. Bernard?
So thank you very much. Have you any question about ITER?
Well, I'm, as you said, the materials person in the panel over here, and I think people underestimate just how hard neutrons are on materials. So we talk about a triple whammy, the fact that they get displaced, the atoms inside the materials, they transmutate, so they change into different types of elements, and of course they have to generate tritium in some instances, or not allow the tritium through in other instances. So Bernard, we haven't talked today about tritium science. We've also not talked about robotics. There are a lot of other technologies associated with fusion. So maybe something from your side on robotics or tritium at ITER?
Yes, certainly. This is two key technology we need to develop, because some of the components are so heavy, so large, no workers will be able to assemble them with the appropriate precision. So robotics is absolutely critical, and is why I am pleased we have an agreement between UKEA and ITER to develop some of the robotics you imagine that the wall to collect the energy coming from the neutrons, okay? When two hydrogen nucleic collide, they produce helium, 5 times more energy, which will contribute to the self-sustained temperature of the plasma and the neutron, 20 times more. And we have 440 tiles with some thin layer of beryllium. And we want to be sure that if any of them got a leak or are suffering for the high collision with the neutron, we may replace it. So it's why we definitively need. Second, the tritium, yes, is why in ITER we have offered to the ITER member to use ITER machine in order to demonstrate that the ITER machine could be self-producing the need of tritium. As you know, tritium is not a natural product in large quantity. Now there is some way to produce tritium, but it could not be sustained if fusion could move at much larger scale. So we are really pleased to do that. Once again, ITER is facing many challenges. From my point of view, the most amazing result so far is that since 2020, the 35 ITER members want to work together and keep their investment in order to demonstrate. And for me, the largest risk for ITER not to be successful would be if an ITER member drop out because they are contributing in kind. They have now 10, 20, 13 years of know-how accumulated. And so, what's pleased me is that, as you know, the 7 ITER members, Japan, South Korea, China, Russia, India, Europe, United States, are not all aligned on any policy. But when it comes to ITER, no politics is involved. It makes me quite confident for the future. And before maybe we go to the question from the public, I will leave the floor to Jane. And how could we bring fusion to commercial reality? Could we do it sooner? As you know, ITER say it will be in 2035. And I learned that some people say 240 and so and so. So how could we accelerate the whole process?
Well, and thank you very much. And acceleration is why my NGO was formed, because we look at fusion from the future backwards. We say fusion as an energy source must happen because we need it for the climate. We need that mitigation opportunity for all of humanity. So if we're looking backwards, we say, what are the hurdles that fusion will face? And I leave it to these many, many brain cells sitting next to me. They're in charge of making sure the devices work, because I have no doubt that between their collective and those who are running any one of a number of the private companies as well as labs, that we'll get there. But the question is, once that device is built, small or large, facing space or facing the production of hydrogen or delivering high heat or delivering electricity, the next hurdle is what I call the hidden valley of death of soft cost. It's the regulatory schemes and it's the finance to carry all of that through. From the financial industries, we've got the beginning of significant private investment, and as you've heard Amanda speak about, the UK is really leading by example on the public side. That'll all be tied together in a if regulatory schemes are more transparent, are more globally aligned, as ITER has offered a perfect example of cooperation. We need to be able to, as we'll just call it with the friendly competition between countries on perhaps fusion devices, we still need that universal set of rules so that parts can be developed in one country and used in another. So I would say that we need transparent and globally cooperative regulation, and we also need more and more finance. I mean, so the quick answer is we need more money, and we need better regulation. Again, we have leaders on the UK end and throughout other countries who've been working on fusion. In the US, we're just starting on that process. And this is where I remind a lot of the early private industry that it's never too early to make a good first impression. And I know that sounds trite, but explaining what fusion is and what fusion isn't. Understanding that fusion is a nuclear technology, but it is not fission, and making sure that you understand the differences. And also making sure that we're patient with the licensing process and the regulatory process. And when I say patient, I mean bringing those who regulate the regulators in, and that's what my NGO does. We work to educate, which is a theme that you've heard everywhere here, educate those who will be future fusion advocates who don't know about fusion yet, who are primarily looking at green energy as defined by renewables, which I love, but we also know we need more. So we need to expand that definition, and we need to make sure they have seats at the table so that they feel as confident as those who are working on the devices themselves, that when we get to a commercially available prototype, that prototype is welcomed to grids, welcome to customers, welcome to utilities, and welcomed by the public.
If I may compliment, as long we have not demonstrated that fusion could work with more energy out of the plasma to maintain its high temperature, 150 million degrees, that we will get from the plasma, it's difficult to accelerate the research. We want to be sure that we are fully qualified when we will start the first plasma. But once it will be demonstrated, I am pretty sure it will speed up very rapidly, is my conviction.
Bernard, can I add to that and the commercialization that it's not an all or nothing. There is a path, and on the path there are multiple technologies to be proven, from superconducting magnets through materials, through robotics, through welding, through modular builds. And so there is plenty of spin-off in broader sectoral spaces across the commercial environment. And so we do encourage folks to understand that you could be part of the fusion journey to the point where we launch commercial fusion, and that there are enormous economic benefits locally, internationally, in being involved in the public-private partnerships in other sectors. The magnets alone taking you into medical imaging, taking you into a high physics lab like CERN. There is a lot of spin-off opportunity. We have reaction engines in the UK, for example, in aerospace propulsion, working on high heat flow materials, and that's come specifically as a spin-off from the UK AEA and the work on diverters where there's high heat flow. So there is a lot to be learned on the way to the final delivery of fusion. Commercialization starts now, folks.
Thank you. It's time now to open the question and answer session. So stand up. Is a micro could circulate? We have a dog. which is knocking to the door. Whoa.
So Bernard brought a friend with him, and
Could you join us? Could you join us?
Spot's excited.
Yes. Okay, I understand. But I have to come and pick up some of the questions already received. But I will give the floor first to the audience.
Yeah, my question was, you talked about tritium being the fuel. I work in a CANDU technology, which starts with heavy water, and tritium is one of our byproducts. We already have technologies that extract that and immobilize it. We largely sell it as helium-3. We immobilize it with a catalyst. But is there partnerships with CANDU technologies? And do you see that partnership expanding in the future as you see that fusion expands and we have more reactors? Thank you.
This is a very good question. Certainly, we are now considering to have some partnership with the people which are producing tritium. And I am sure you know, Canada is leading, as well as South Korea and Romania. Not so many, okay? So, we have recently signed an agreement with Canada in such a way Canada agreed to sell us their tritium stock before we demonstrate the capacity of self-production. But beyond that, we need a lot to take advantage of their knowledge. Science and hydrogen fusion has no border. We need to bring in all the best experience for that.
may I add to that? I mean, of course, we need to be able to breed our tritium ourselves to let a fusion power plant running. But for the first stock, to first fuel it the first time, and if you have many, we would very much rely on that. So we are very interested in have tritium from the CANDU reactors.
My long-term vision is that the world energy supply will be made of only of renewable energy coming from the sun and the hydrogen fusion in a very complementary way. As you know, the fission power plant, they produce some radioactive material which could be stored for quite long. So it's why my dream, when hydrogen fusion will be well established, we will make it only renewable and fusion energy in the most complementary way. It is my term. In the meantime, never get rid of something which is working as long as renewable and hydrogen fusion has not shown their capacity to fulfill all the world energy supply. Keep on with all the clean energy. So far, I know there is several perception, but I prefer we prevent to burn coal, to burn gas when we see the gas price rocketing in a few days because people need it, is my perception. Any other question?
Thank you. Simon Harrison from Mott MacDonald and the Institution of Engineering and Technology. I was struck in your presentations by the analogies with the history of space exploration and the massive public sector investment to solve the fundamental challenges, the spin-outs that come from that, but then the times 10 cost, time, performance escalations that you get from Silicon Valley, essentially. And I just wondered what parallels you might draw and learn from the space program. and history of that?
Do you want any of us? Hi.
Well, from the U.S. perspective and from watching the private fusion industry develop, not only are they in intellectual partnership with a lot of the now private space exploration, but I think we've discussed, for instance, the spin-outs, the economic lift that can come from the engine of fusion coming to the grid has the potential to equal or surpass what came out of, for instance, the Apollo project. In the U.S., we often call our fusion mission a moonshot. And obviously, the timing is different, but the global goal, one of our colleagues here calls it a World War Zero, right? So our climate mission is greater than, for instance, any of the inspirations that launched our space mission. I don't know that I got exactly to the point of your question, but I think we can draw parallels. I think we're going to also see economic benefits that probably way surpass what we saw coming out of the early space industry. And who knows, fusion may actually be the choice of fuel for our next rockets.
Annika, yes.
Thank you, Bernard. I also just wanted to add, not everything worked with all the different approaches to space exploration, right? And I think fusion is very similar in that not all of these, we've got so many different approaches going on, not all of them are going to work. And as a community, we need to be transparent about that and not be afraid of failure, because as long as, even if just one works, that's all we need, right? So to be very transparent and not fear failure, I think, is one of the main lessons that we need to learn from space exploration.
I couldn't agree with you more. Fear of failure could be our greatest challenge.
Could I take a third angle on that? You were talking also from an economic point of view, and I think economies of scale play here. Space was on its own for a long while, but it struck us how many parallels there are with fusion these days. If we're talking about things like thermal gradients from cryogenic all the way up to high heat load, fusion has a lot in common with aerospace at this moment in time. Rad-hard materials for our diagnostics. Anything that is exposed to cosmic rays and solar energetic particles is needing rad-hard protection. So in terms of thermal shielding, in terms of diagnostics, we've got a lot of overlaps. And I think the more industries that are playing together, that brings the R&D costs down, and particularly that first barrier to entry for your supply, your niche supply market. So hopefully there we will benefit from the fact that we're joining space and that we're not competing with space.
The lesson I have learned as a ITER organization director general from the space, never compromise with safety. Rush is a way to fail. Second, never compromise with quality control all the way along. And listen to any of the stakeholders if you feel there is some risk in the way you do. So, from my point of view, there is a lot of similarity, but there is also quite big challenge, you know. In the case of the space, you have a huge amount of energy when the launcher is, okay, take off. Myself, I progressively, you understand? I control the plasma. If anything go wrong, I stop immediately. No runaway. It is intrinsically safe. So from my point of view, I have a little bit luckier than the people which are in charge to demonstrate a new launcher or a new satellite. So I guess we are near the end. Is it correct? Yes, good.
Yeah, so my question, it's kind of to all of you really. We saw during the pandemic that if governments dropped some of the economic barriers and some of the political barriers, we can achieve things very quickly. You know, we found the COVID vaccine much quicker than we would find normal vaccines due to those barriers being removed. So I appreciate it's probably hard to answer, but if governments were to treat the climate emergency in a similar way to how they treated the pandemic, what do you think is the quickest and the soonest we'd be able to achieve, you know, commercial fusion?
It's a very good question. You know, 6 years ago, when I visited the US Congress, they told me, if we give you all the money you need, could you make it sooner? And I was very frank. As long as I have not assembled the vacuum vessel, the coils, and demonstrate that I produce at least 5 to 10 times more energy in the plasma, I want to be humble. Just to let you know, very recently, my people has been able to assemble a vacuum vessel sector like a quarter of an orange. Nearly 450 tons of double-wall steel. Very complicated shape with a thermal shielding because the temperature of the vacuum vessel sector will be 250 degrees, and 5 centimeters later the superconducting will be minus 270 degrees. So it was very challenging to cope with the specification. The specification was that on all the interface, nearly 60 linear meter, no deviation larger than 2 millimeter. We achieved 1.4. It was a result of the manufacturing, of the metrology, of the engineering everywhere. So, from my point of view, you know, I am a scientist. I don't want to sell something I don't believe is still there. But it does not prevent me to work very hard, day and night, to lose my voice in order to move forward.
Yeah, I mean, Bernard explains the challenges, and this is certainly true, and that means that you cannot just buy any amount of money by any time. I mean, not coming close to tomorrow, right? But still, what you could do now, I mean, now that we learned how to build ITER, if you would really not be afraid of failures and you would put a lot of money, what you could do then next step is to just let ITER go and operate, and then in parallel design a power plant, learning how you build ITER, and then operate ITER, and then go ahead with a power plant. And if you even had more money, then you do this for the tokamak and accelerator. And then still it would be much earlier than now in our roadmaps, that we first wait until ITER had achieved the self-heating state, and then only we start designing a power plant. We do design it already now, but to start building. So if you take higher risk, you could say, okay, I learned how to build the device now. This is ITER is good for. You operate it in parallel while you're already building your power plant. This is possible, and you could, as I said, already go for the 2 concepts that are most advanced. So yes, you can buy time, but not infinite, right?
So, yes.
Yeah, just one small.
Annika.
Thank you, Bernard.
0.42.
I'll be fast. So with the COVID vaccines as an example, that's a really good one. They didn't make those, progresses just in the last year. They've been working on that 10 years previously. They've had those investments 10 years previously. So I'd say we're at that stage now where we're making those investments, and then hopefully we'll be there, sooner rather than later. But yeah, it's a lot of work going on beforehand from the final product.
Coming back to the space, the space had many try and some failure. I would like first try for fusion power, first success. So it's why I prefer to take care of the soundest way to proceed. And to complete, very short question. It's clear that is the new generation which will operate ITER, which will operate the new fusion power devices. We need to attract the new generation. And people have to understand, he's not specialist of fusion physics, electronics, mechanical, project management, many opportunity. So we have launched a large program in order to attract from everywhere in the world the most qualified postdoc and internship. We count on the new generation. So thank you. We are a little bit behind schedule. I hope that we will not be behind schedule when it will come to complement renewable energy and to have a full, sustained, clean, safe energy. Thank you all for your patience, and we hope someday you will visit the ITER site, the UKE site, the IPP, whatever you want. Also the D3D, in order to understand hydrogen fusion is no longer a dream. It is a real project management.